tiny fraction of the objects in the Oort cloud. And so what's happened in the last 2 decades is that there's been a fantastic burst of science based on the Kuiper belt, simply because we can observe objects before they come in. So here's this diagram that summarizes what's known about the Kuiper belt, what's observed. Here's the distance from the sun. Here's the orbital eccentricity. 0 is a circular orbit, 0.8 is eccentric. You can see that the Kuiper belt objects are not uniformly spread all over this diagram. They seem to belong to different families or different groups, and not just because I gave them different colors. They're intrinsically different objects. And this was not expected, but it's a very solid result that emerged immediately in 1993 and 1994, and has just grown stronger ever since. So I won't talk much about these populations, except to say that these guys are Kuiper belt objects that encounter Neptune occasionally and are kicked by Neptune outwards into large looping orbits, eventually to escape the solar system over there. So those are called scattered Kuiper belt objects. And these blue guys are in special resonant locations. The ratio of their orbit period to Neptune's orbit period is the ratio of small integers. And that special resonant relationship gives them dynamical stability, long-term dynamical stability. So the most famous one of these is Pluto, which of course is that one right there. And Pluto, like all the objects above that black line, is smart enough to know that it can come inside Neptune's orbit, but only when Neptune is 90 degrees away. And so it has a phase relationship with Neptune that prevents close encounters. Because Neptune is the massive object, 16 Earth masses, it scatters everything away. So those are the populations that have been identified in the Kuiper belt, different resonances. These are Trojans, these are the Plutinos, those are the 2-to-1s right there. So why do I mention that? Well, it'll come back in just a moment to give one of the most important constraints from the Kuiper belt. So here's a basic summary. The distances of Kuiper belt objects go from the orbit of Neptune out. We see some going out to 2,000 AU, probably there are larger aphelion distances than that. The number of objects is a few billion, probably. The mass of Kuiper belt objects is pathetically small. So if you add them all together, it's only 1/10 of an Earth mass at the moment. And that's a big problem, actually, because if you spread 1/10 of an Earth mass of objects over the volume of the Kuiper belt and ask how long would it take for those objects to grow collisionally, the answer is longer than the age of the solar system. And so the belief is that although we have only 1/10 of an Earth mass now, it's a remnant population. That the original population was much, much larger, probably hundreds, maybe 1,000 times the current population, so that the collision rate was much, much larger, and these objects could grow in an appropriately short time. So we think that the Kuiper belt now is a fossil of what it was in the beginning. We think it's a dynamical fossil of the formation of the solar system. So, actually, Wing Ip is not here today, but Wing Ip and Julio Fernandez were the first people to suggest that the planets didn't form in their current orbits, that they migrated radially in response to a torque. The torque comes from ejection. When a planet ejects a comet from the solar system, it's throwing away mass, but it's also throwing away some energy and some angular momentum. And so the orbit of the planet can change size. It turns out this is the only way, planetary migration is the only way we know that can provide a large population to the resonances. So the observation in the Kuiper belt that the resonances are heavily occupied gives basically incontrovertible evidence that the planets migrated. So actually, I think maybe the biggest consequence of the discovery of Kuiper belt is that, the finding that the planets must have migrated. So Neptune, which is now 30, maybe was born at 15 AUs from the sun. The whole solar system was compact in the beginning compared to now. So we have a couple of things. The resonances are important. Neptune formed somewhere else and radially migrated, and there used to be a lot more stuff than there is now in the Kuiper belt. These ideas were put together in this model called the NICE model by Gomez and other people, about a decade old now. And I'll just show you this. It's a movie. Here's the semi-major axis, the distance from the sun. Here's the eccentricity again, circular orbits at the bottom, elliptical at the top. Here are the major planets, 1, 2, 3, 4, not at their current locations. So currently, Jupiter is at 5, Saturn is at 10, Uranus is at 20, and Neptune is at 30. So this is a compact solar system. And in this model, the Kuiper belt is represented by a row of green dots. And the row of green dots is assumed to carry about 30 Earth masses of stuff. So 300 times the mass of the current Kuiper belt. So what this model does is just follow the gravitational tugs by these planets on these objects here, and the back reactions on the planets caused by scattering events. So we'll just start the movie. So immediately you see that Kuiper belt objects out here are pumped up from this flat circular set of orbits here by interactions primarily with the outermost planet. And the outermost planet kicks objects up into this arc, which we see in the real Kuiper belt. So we see these scattered Kuiper belt objects. You see the beginnings of vertical structure, like the resonances that we see in the real distribution of Kuiper belt objects. And we see a cold region out there where the effect of the outermost planet is small. And then we see these flashing dots. Those are objects that are very short-lived. They're just there for one integration. This is 10 million years per second. And we see the planets jumping because every time they eject a comet, they have a back reaction that pushes them in the opposite direction. They're jumping, but they're also drifting. And these two are drifting into a mean motion resonance. So Jupiter and Saturn are moving to a mean motion resonance. And when they do, something very severe happens. The Kuiper belt explodes in this model. And the explosion occurs because a planet, which we would now call Neptune, has been thrown into it. So it's like throwing a brick, I always say, like throwing a brick into a nest of bees. The bees get angry, they buzz out. And this then would correspond to the process that lost 99.9% of the mass from the Kuiper belt. Most of this stuff is ejected outwards. A lot more is showered into the inner solar system, eventually to hit the sun, and sometimes to hit some planets. And the claim is made that this event was responsible for what's called the late heavy bombardment, which is a time at about 3.8 billion years ago, when some people believe the inner solar system was showered with an extra high density of projectiles. So the point of showing this is not that this model is correct. So we have no evidence that this is correct, but that it might be correct. And so what's happened is that the old models of the solar system, which basically were always the same, everything just moved in circles forever, have been replaced by models in which there can be strong dynamical chaos, and strange and unexpected and weird and wonderful things can happen. So the people who make these models claim that many of the subpopulations that appeared in those boxes that I showed you can also be explained by this clearing event in the Kuiper belt. So we know that the planets have lots of irregular satellites. We know that there are Trojans. These are bodies that move in the orbits of giant planets, but are resonant with them, so they never interact closely with the giant planets. The Jovian Trojans, for example, are 60 degrees ahead of and 60 degrees behind Jupiter. This is a satellite of Saturn called Phoebe, is a big one, 200 kilometers. That may have been a Kuiper belt object that was captured in this early phase of solar system clearing. And maybe some objects in the outer belt could be captured that way, and so on. So the models have changed from being simple, repetitive models of the solar system explaining a few features to very grandiose models that try to explain everything with a few simple events and a massive amount of computing power. Now we do know that a great many Kuiper belt objects are binaries, and we have very special constraints from binaries. They're double Kuiper belt objects. Some are wide, some are narrow. What we know from the binaries, and I'll have to go over this very quickly, what we know from the binaries is that the collisional environment in the Kuiper belt cannot have been very, very brutal. Otherwise, these binaries would have been split apart. The wide binaries in particular are very loosely held together by gravity, and a strongly collisional history for the solar system would have split them apart. So the fact that they exist sets an upper limit to the collisional history of the solar system. On the other hand, we have binaries like that, and those binaries would not form in any kind of a hot environment. So these binaries argue in the other direction for a very, very dynamically cold solar system, in which the relative velocities between the initial components were small, and in fact we think these components might have come together under the action of what's called dynamical friction, where two bodies are interacting with a sea of other bodies nearby, moving at very low speeds relative to them. So the existence of binaries tells us something about the collisional history of the solar system. We're still working that out, but we do see that certain places in the Kuiper Belt have probably close to 100% binary fraction. And then we have some kind of a constraint from the size distribution. So the size, this is basically number of objects against how big the object is. This is the thing that's been measured now for almost 20 years. It hasn't changed much in the middle, but the end parts are changing, especially the small end, because we can measure fairly small objects. What we think is that the small objects in the Kuiper Belt have been affected by collisions, and so Kuiper Belt objects can collide. When they collide, the speed difference between them is 2 kilometers per second or something. They can smash, and the fragments may be the nuclei of comets. The comets may be created by this kind of collision, whereas the big guys are probably primordial accretion products. Skip over that too. Let me just do this and then we'll move to the comet. Okay, so we have in the solar system evidence from magnesium-26 of the past presence of aluminum-26. Typhoon Lee, right there. You're the man. The surprise is that we would have any evidence for aluminum-26. This is a short-lived element. Half-life is like 1 million years. And it could be produced in the early sun, but it's certainly produced in exploding stars. And so the usual interpretation is that the solar system was seeded with this radioactive material, and the radioactive material was trapped almost immediately in rocks, in asteroids, that we now possess as meteorites, and so that's how we know about it. But to make this happen, it suggests that there were massive stars nearby. Now, if you look in the sky now, there are no massive stars nearby. Massive stars don't live long, and so they're rare, and they tend to be found only at large distances. So this is very, very suggestive of the sun's past membership of a cluster, like the cluster that we saw in the beginning from the Genes collapse cloud. So that's one constraint. We also know that the solar system would be busted apart if another star had come within 100 AU of the sun. So Neptune would have been destabilized, Kuiper Belt wouldn't look the way it looks if another star came very close. So that sets kind of an upper limit on the density of stars in the cluster from which the sun formed. The Kuiper Belt classical part has an edge at about 47, 48 AU. That would not exist, probably, if a star had been closer than about 200 AU. So we have another constraint on the collisional environment, the stellar collisional environment of the whole solar system. And the fact, just skip to the bottom, the fact that the solar system was not completely, immediately photoionized and ablated away by the strong radiation from massive stars nearby sets an upper limit to the number of massive stars. So if you put all these constraints together, as Fred Adams did a few years ago, you basically find the following: that you can constrain the number of stars per unit volume multiplied by the amount of time that they were nearby. And the constraint is 80,000 stars per cubic parsec times 1 million years. And the total number of stars you also can constrain to be about 4,000. So those are consistent with the kinds of clusters that we see in the sky. These constraints are satisfied. For example, you could have 4,000 stars in 1 cubic parsec for 20 million years. 4,000 times 20 is 80,000. That would be consistent with the constraints we have. Or 4,000 stars in a somewhat larger cluster of 10 cubic parsecs for a longer time. So we have these constraints on a cluster that no longer exists and which will never be found because the stars are now completely dispersed around the galaxy. It's pretty cool. Now I'm going to quit that and go over to this other subject, because at lunchtime that seemed to be a good idea. So you know that a spacecraft has been sent to a comet, and the comet is called that. It's a horrible name, although these are both very nice people, I'm sure. So let's call it 67P. This is a comet which we know from its orbit is called a Jupiter family comet. It came from the Kuiper Belt. So the orbit is small. The radius of the orbit is about 3.5 AU. The eccentricity is modest. It's about 0.6. The inclination is small. It's about 7 degrees. It's not a long period comet. It's not coming from the Oort cloud, that's for sure. It's a couple of kilometers across, and it's the target of this mission, and that is Churyumov, and that is not Churyumov. And Gerasimenko has never been seen. So the second person, doesn't go to meetings, and so she's never seen. She exists, she's still alive, but she's not observed. There's the Rosetta Stone. You familiar with that? I think I'll just skip over. I'll skip over that. Okay, and here's this diagram, which I like because it shows the size of the nucleus compared to the size of Los Angeles. It's about, which is where I live, it's about 4 kilometers across. Okay, now I'll just skip over the next couple to save some time. There's various cities being destroyed by German scientists with the comet nucleus. And here's what the spacecraft has done. So the gravity of the nucleus is so small that you can't use it to go into orbit unless you're very close. So this is a spacecraft that contains ion thrusters. It expels ionized gas and uses that to make a force. The force produced by the ion thrusters is less than 1 Newton, very, very small, less than 1 Newton. A much larger force is exerted on the spacecraft by, a comparable force is exerted by radiation pressure. It has these big wings, and the sun is pushing on the wings all the time. So they're firing this rocket, this ion thruster, to kind of shadow the motion of the nucleus until the end when they go in very close, and then they can begin to use the gravity of the nucleus, the 2-kilometer body. It has a mass of 10 to the 13 kilograms, and the density of the nucleus is about 400 kilograms per cubic meter, so it's less than half the density of water, indicating that it's a porous body. It's got lots of empty space inside it. So when they get close, they can do what look like more normal orbits around this thing. Okay, so that's the basic idea of the Rosetta mission. Hover around it when it's a large distance from the sun, follow it as it moves in towards the sun, and as the activity begins to grow, you can monitor the way in which the nucleus changes as a result of sublimation. Okay, there are various things that I also will skip over to save time, so we can get to the picture. Here we go. So here's a sequence of pictures from the orbiting spacecraft. And so you can see it's a very strange shaped object. It's not spherical. And in fact, it looks immediately in this picture like it might be 2 things stuck together. One thing and another thing. This is 4 kilometers across here. This one is roughly 2 kilometers like that. And this is a hole. This is a big notch. So it's 2 things maybe separated by a bridge. So immediately the question is, why would that be? So one idea is that this was a Kuiper Belt object, that's for sure. Maybe it was a binary Kuiper Belt object. Maybe that's what a binary Kuiper Belt object looks like after the components have nestled down together. That's possible. Another idea is that this thing in the beginning was more spherical, and it's undergone selective mass loss from this region. So the sublimation may be happening here, but not here. So whatever was in there has been ejected. So the physical picture there is, at least for me, the physical picture is to start with an apple, and then eat the apple, rotate the apple as you eat it, and what you end up with is an apple core. With one end, the stem comes out here, here's one part, here's the part that you ate through the middle. So perhaps it's uneven insulation, solar heating of the nucleus that caused this, or perhaps it's a binary. The spin axis is like that. So the spin axis corresponds to the maximum moment of inertia and the minimum energy, which is kind of what you'd expect. That's a nice result. So spinning around there like that. We'll see some more interesting pictures. Okay, so now we're looking down on one end, and you can begin to see there are these circular features which look like impact craters, and then we can see dusty regions on the surface. This is a smooth plane on the surface of the nucleus. But the trouble is, they're not impact craters, so they don't have the right shape, profile, and they don't have the right distribution. The relative numbers of large and small are inconsistent with any impact population that we know about. So these are something else. They're not impact craters like you see on the moon. They're maybe related to the activity itself. Maybe the vents that release material are producing these features. And the surprising thing about seeing a lake of dust is that the gravity on this body is 10 to the minus 5 times the Earth's gravity. And the escape velocity is 10 to the minus 4 times the escape velocity. On the Earth, escape velocity is 10 kilometers per second. On this body is 1 meter per second. And so somehow dust can still be held by this body and can pool into gravitational low regions on the surface. Okay, so we'll just take a few more looks at this thing. The orientation of the spacecraft changes, and the sun, of course, is changing. Here's a sideways view showing this big notch which goes all the way around, and there's one component and a second component. And then we begin to see that in the middle is this smooth material, which is like that dust lake that we just saw on the end. That's a big crater form there, a big crater form there, and then this sharp wall that comes down into the valley in between. So the big deal about this is that, you know, there are many, many geologists who look at these pictures and have nothing at all to say, because because this kind of geology has never been seen before. It's not the kind of geology you see on a terrestrial planet, at least not superficially. And so literally people at the moment don't know what this means. They don't know how to interpret these features at all. And that's good for me because I can say anything I want. And so I think that these are indeed features caused by mass loss. So I think this is an ice-containing comet in which mass is lost from certain regions. We know that the comet is very, very dark. The albedo is like 4%. It's basically blacker than anything in this room. And that's because its surface is not made of ice. It's got a layer of dirt, refractory material on the surface. And the ice is just beneath the surface. And I think the ice is, has sublimated from here and made this circular vent in here, and there are other features that make that even more obvious. But not everything that's ejected from a vent can escape from the body. A lot of the stuff falls back on the surface, even though the escape speed is so small, and flows over the surface. So you can see, in addition, that there are some quite big boulders. So these are 20, 30, 40, 50 meter sized boulders on the surface. So big blocks of stuff, which itself is very surprising because the model of the comet is that it formed in the outer solar system in a very, very gentle environment. And it has this very low density because it's very porous, and it's probably very, very weak. We think the tensile strength is probably 100 newtons per square meter. It's about 10 to the minus 3 of an atmosphere. And yet, at the same time, it's able to have these big clumps of stuff that somehow must have either grown as independent planetesimals or be pieces of kind of bedrock material that's eroded off. So there are many, many just strange, weird, and wonderful things. Here's the central saddle showing how smooth that is. So that's the gravitational minimum, and a lot of stuff can collect into this place. And we go closer. That's a nice one. We go closer and get better and better pictures. And the main spacecraft is carrying in a 1 meter sized secondary spacecraft which is dropped onto the surface. So it moves in, it makes maps and pictures of the surface, and then moves in from 60 kilometers into, I think, 10, and then drops this secondary spacecraft called Philly, like a small refrigerator with 3 legs, onto the surface, after deciding where to go. Here's a big scar. You know, this is material that's been eaten out by sublimation, causing the surface to collapse in. So the whole thing is just amazing. Here it looks like flows of dust. Material has slurped out of that crater under basically microgravity. Here are some very peculiar features that look like eroded volcanoes that you see in Utah and Arizona in the US. There's a hard plug of material and then a slope of debris on either side. There's one, there's another one, there's another one, there's another one, there's another one. And in fact, there are many of those, like a spiky hedgehog. Here are some of those building-sized boulders on the surface sitting on a lake of dust. So these are by far the best pictures of a comet nucleus ever obtained, and also by far the most mysterious. And if anybody in the audience knows in detail what we're looking at, please write a paper about that very, very quickly. Okay, so the lander, let's get to that and have some questions. The landing sites that were chosen were picked to be smooth and simple. But in fact, there's no place on the surface, it turns out. When you go close enough, there's no place on the surface which is smooth and simple. So there was no really good choice. But they picked J, which is this one, and plopped the lander down on it. Here's a close-up of the landing site. Here's the X that shows where they hoped to land. Fairly flat, but it's not that flat. And the spacecraft simply falls, here's a better picture, the spacecraft simply falls onto the surface under gravity. The escape speed is a meter per second, so the hit speed is a meter per second, it's very, very small. And the idea was to fire harpoons into the surface to try to hold the spacecraft down. And what happened was a little bit different. So here's what people think might be an image of the touchdown. So this is the before picture, and then there's a micro movie that shows the before and the after. So this black splotch may be the shadow of the dust cloud kicked up by Philly hitting the surface. And this little black splotch right there may be the shadow of Philly itself after it bounced off the surface because its harpoons did not fire. These other things are bad pixels in the data, but that's probably the shadow of the dust, and that's probably the shadow of the spacecraft on the surface. And so we also have this picture, which shows a close-up of where Philly might have hit. So take a look at that, and I need you to remember the exact locations of all these boulders. No, I'm just kidding. So this is the before picture. The scale is about here, 2 meters, something like that. And here are features which suddenly appeared from nowhere. These guys were not there at all, and now they're there. Whereas this is a pre-existing crater, and so is this, and these other boulders. And so these features changed before and after the impact of the landing spacecraft. But the lander only has 3 feet, but there are more than 3 holes in the ground. So the truth is nobody knows what happened. Something happened, but we don't know what. But that might be where it touched down. This is one of the nicest pictures they've made so far. So here is a piece of the surface. Here's the time, 1514. Here's the spacecraft on its way down. The refrigerator with 3 legs on its way down. 1514, 1519, 1523. And then here are those 2 pictures that I just showed you as a blink pair, before and after. And then the one that's really cool is at 1543. The spacecraft actually is here and is leaving the picture. It's off, it bounced off the surface. So there is, as I was saying at lunchtime, there is an internal memo, which I happen to have seen, in which the spacecraft experimenters say, too bad we didn't test those harpoons in a vacuum. So it touched down and they couldn't stick.